Today's lesson is the first lesson in chapter 4, all about extreme values of a function. And we're also going to learn about the extreme value theorem. Okay, well, first of all, chapter 4 is all about applications of derivatives. So we're going to see how derivatives are used to find minimums and maximums of different functions. And that's what extreme values are, minimums and maximums. All right, so there are two kinds of extreme values, two kinds of minimums and maximums. One is an absolute minimum or maximum. It's also called a global, and our book just calls it a max and a min. All right, so this extreme value, those are the absolute highest y value on a function. Okay, so the absolute highest y value. Now, in between, there could be lots of zigs and zags in a function. Let's say a function goes like this, and these would be considered local minimums or maximums unless they're the highest one, and then those are considered the absolute, the global, or just the biggest maximum. Okay, so we're going to look at a function, x squared plus 1. And we've graphed it over here, and we're going to look at the maximum and minimum depending on what the interval is. Okay, so depending on what this interval is, we're going to look at the maximum or minimum. All right, so if you're going from negative infinity to positive infinity, there is actually no maximum on here. Okay, there is no global maximum on here because it goes to infinity. Now, there is, though, a global minimum, and it occurs at 0, 1. So the minimum, is actually 1. All right, and that's your minimum. Y equals 1. All right, now if we limit our interval from -1 to 2, that's where these two green points are, -1 to 2. Our minimum, our absolute minimum in that interval is still 0, 1. But our maximum in that interval now is at 2, 5 because that's the highest point. Okay, so y equals 5 is our maximum value. Now, if we make a new interval from -1 to 2, but we don't include -1, I think we still have the same answer as we did before because our maximum is still 2, 5 and our absolute minimum is 0, 1. Okay, so one last iteration of this. What if we take out the -1 or we take out the -1 part of the interval and we take out the 2 part of the interval? All right, we cannot tell what our maximum is right now because we have a hole there. And we cannot name that hole because we get closer and closer and closer to it. And you can always squeak a little bit closer without being on it. So there's no way to name a maximum. And then our minimum is still 0, 1. All right, so that's how we find global minimums and maximums. And one more time, our book calls them maximum and minimum. So just so that you know that as we go along. All right, now we're going to talk about the extreme value theorem. And this theorem is really an existence theorem. It says that if you have a function, and there are some important parts of this definition too, of the extreme value theorem. It says if you have a function that's continuous, if it's on a closed interval, then you are guaranteed to have an absolute maximum and an absolute minimum on the interval. Okay? It has to be continuous. It has to be a closed interval. And also, we always consider those endpoints when we do that. So the question we have is, does the extreme value theorem apply to these functions? All right, so basically we're asking, is it continuous? Is it closed? This one, the answer is yes. It's continuous and closed. This one, continuous and closed, nada, no. So the EVT applies to this one. We call it the extreme value theorem, EVT, because it's easier to say. All right, so, and so this function has extreme values. The highest point would be up here. The minimum point would be down here. Now, this second graph has a maximum. So you can have a maximum even though you don't have an extreme value theorem. And it looks like we even have a minimum, a min and a max. But we're not guaranteed one. Okay, so in this function, we're guaranteed one. In this one, it just happens that we have one. But the EVT does not apply here. No EVT. Okay. In your book, it also talks about what are called local minimums and local maximums. They could also be called relative maximums and minimums. That means that at that area of the curve, you have a maximum, or at that area of the curve, you have a minimum. All right, so local extrema also include endpoints if the function exists at the endpoints. So here and here, we would definitely have local extrema, and also at all the other points that are listed on the graph. And this note is a continuous and a closed interval, so we are guaranteed, what do you call it, global or absolute maximums. We are guaranteed them. Okay, so let's look at our minimums first. We have two minimums. They're equal. There's no other point lower on the graph. These two are absolute minimums. They're both absolute because they have the same value. Absolute minimums. They're also local minimums because in that area they're both the minimum values. Okay, so up, and then let's also, let's see, we also have, we have another minimum over here too, because this is a minimum because the graph is going up to the left of it. So this endpoint is also a minimum because the points around it are bigger than it. Okay, so this is considered a local min. Okay, so let's then look at the two maximums. These are both maximums. One is bigger than the other, so this one we're going to call a local max. This one we will call an absolute or global max. Okay, so that's what we have for maximums. And that's your lesson on global maximums and minimums and local maximums and minimums. The beginning of chapter 4.